Bricks have been around since 7000 before Christ, making them one of the oldest building materials known. They were found in southern Turkey, near the city of Jericho, at the site of an ancient town. In places with warm weather, the first bricks were made of mud dried in the sun. In ancient Egypt, bricks were made of straw and clay. Today, the proof of this is seen at the ruins of Mohenjo-Daro and Harappa. On the walls of the tombs in Thebes, there are paintings of Egyptian slaves shaping, mixing, and carrying clay to make bricks that will dry in the sun. Around 4400 before Christ, the first fired bricks were found in a walled Daxi culture settlement called Chengtushan. However, it wasn't until 3500 before Christ that fired bricks gained a lot of interest. This was, no doubt, the biggest step into the future. From then on, bricks could be made without the heat from the sun. They quickly became popular in places that don't get as hot. These bricks were made from red clay, baked at over 600 degrees Celsius on all sides, and used as home flooring. By the Kujiling period, 3300 before Christ, roads and building foundations at Chengtushan were made of fired bricks. Thousands of years later, scientists are looking at the possibility of replacing lithium batteries with fire bricks. Lithium-ion batteries are great at storing energy, but this ability slowly disappears as they are charged and drained repeatedly. Keeping energy stored is quickly becoming one of the biggest problems of the 21st century. The cheapest sources of clean energy are hard to predict, so we have to store the energy while it's being made so we can use it when we need it. In this video, we see how 3000-degree bricks will end battery storage soon. Lithium-ion batteries store energy in places as small as people's homes and as big as huge ones that are directly connected to the grid. But storing energy this way on a larger and larger scale is expensive and can be bad for the environment. So, what effort are scientists pulling to solve this problem? Researchers at MIT, Massachusetts Institute of Technology, are looking at the old technology of fire bricks again to see if it can help the world switch from fossil fuels to renewable energy. The researchers devised a way to turn extra electricity made when the wind blows or the sun shines into heat that could be stored in fire bricks for later use. Their firebrick resistance heated energy storage, or FIRE system, costs 1/10 to 1/40th the price of pumped hydroelectric systems or batteries. How does the FIRE system work? Excess electricity is converted to heat by electric resistance heaters, which are then stored in a vast mass of firebricks. According to their findings, they can keep the heat for extended periods when the firebricks are contained within an insulated casing. The heat could be used in industrial operations or later converted back to power. Regis Matsi, retired Westinghouse Electric Chief Technical Officer, was not involved in the research. However, he told MIT that how electricity prices are determined in the US results in a skewed electricity market with low or even hostile prices when renewable energies supply a significant portion of the grid. He believes fires could provide a novel answer. Nonetheless, he insists that a demonstration would be required to determine whether the technology is actually cost-effective. The Electricity Journal published the MIT study online at the end of August. The next phase will be to build full-scale prototypes in the real world, which lead author Charles Forsberg anticipates will happen in 2020. He stated that they are seeking the proper customers, citing an ethanol factory as an example, because they use a lot of heat and are located near a huge wind farm. Rondo Energy is yet another outlet trying to avoid the problem. So, how does Rondo Energy avoid this issue? And what makes their technology so unique that Bill Gates' clean energy funds are interested in it? Some systems use mechanical or gravitational energy, but Rondo uses thermal energy, which is very handy if you want to heat something. Many other thermal storage methods exist, but at the end of this video, you'll understand why this one is unique. The first major problem with most thermal storage devices is that they are excessively cold. This is a concern for many thermal storage applications. This is because they retain less energy and can't supply heat at the needed temperatures. Interestingly, steam near or more than 1000 degrees Celsius is frequently required for industrial heat while working with steel, cement, fertilizers, and ethylene. Some of Rondo Energy's investors are cement makers. Apparently, their approach will contribute a large early step in reducing cost at a reasonable level. Although we rarely think of industrial heat in our daily lives, it accounts for a significant portion of worldwide energy usage. In fact, industrial applications account for more than 30% of overall greenhouse gas emissions, with heating accounting for more than 70% of those emissions. No doubt, this is a huge challenge to industrial heating processes. And, while batteries could be used to store electricity that is subsequently utilized to heat up steam to the requisite temperatures, they are nearly always prohibitively expensive. However, the Rondo heat battery combines inexpensive renewable energy with cheap storage, making this green option less expensive than natural gas. This is a win-win situation in many worldwide marketplaces, especially given that this is a difficult to decarbonize industry. We now understand why the Rondo heat battery is so useful. Let's see how the technology works. Although this system is generally straightforward to grasp, some fascinating engineering is going on behind the scenes. The intermittent energy from the grid enters the system and drives electrical heaters, which heat the bricks in an echo heating chamber. After the bricks have been heated and the system has been charged, air can be blown over those bricks to be heated up before being used to heat steam in a heat exchanger for continuous usage in industrial applications. The best part is that these are all tried and true technologies from other industries that Rondo is putting to use in a fresh way. Their core idea is based on the understanding of basic physics, followed by the system design and its applications. The main innovation is the previously described echo heating chamber. That was the innovation that enabled the development of a heat battery that is extremely low in cost, extremely efficient, and capable of delivering almost 95% of all industrial heat used globally. The bricks and heater are located in the echo chamber, where they radiate heat to one another and bounce around like an echo. Actually, this is what allows the system to function. Most other heat battery technologies use a fluid, such as water or air, to heat the storage mass, which could be sand or rocks. However, because heat is sluggish to transmit through the storage medium, this process necessitates turbo equipment and results in hot patches within the battery. Both of these constrain the operating temperature and the pace at which the system can be charged and discharged. One thing that has been observed in power grids all across the world is that the faster you can charge, the more advantage you can bring to the grid. The radiation equation explains why the radiation echo chamber works. The first three terms are the Stefan-Boltzmann constant, material emissivity, and surface area. What is essential is that the temperature variables are raised to the fourth power. This implies that if one brick is even slightly colder than another, a large quantity of heat will be transferred to it by radiation, allowing for uniform heating and no hot spots. Because of the extraordinarily high temperatures enabled by this technology, the system can have energy densities as high as lithium-ion batteries at roughly 260 watt-hours per kilogram. However, because the energy stored is related to the change in temperature, we can only attain this total energy density by discharging the battery much below the 1000 degrees Celsius output that we require. As a result, Rondo can employ a two-stack technique, in which one heat battery can be fully discharged to temperatures well below 1000 degrees, and used to preheat the air before entering a second stack and heating to the needed temperature for the steam. Rondo employs dynamic insulation. The heated bricks are surrounded by a double wall with an air gap between them. This is comparable to double glazing, which employs argon gas between the two panes since argon conducts heat poorly. The fact that the air in the air gap circulates around the entire system before being routed via the heat battery and over the hot bricks makes Rondo's installation dynamic. This means that the last layer of insulation will only have to contend with temperatures around 150 degrees rather than around 1,500 degrees within the actual chamber. Despite the fact that industrial heat is certainly a large enough industry to tackle on its own, Rondo's heat battery might be employed in other scenarios, such as district heating, in which thermal energy is saved and provided to residences via a heating network. That's all on how 3,000-degree bricks will end battery storage. What do you think? Is this a sustainable invention? Do you expect scientists to do more and curtail any unforeseen loopholes that might appear in the future? Are you excited about the development? Let us know your observation and ideas in the comment section below. If this video is insightful, please go on and like this video. Remember to subscribe to our channel and click on the bell button for more updates.